Good evening. I'm going to do a little demonstration on the spring force. So I have here a spring attached to a force sensor. The force sensor is the vernier sensor, so we'll use that for the moment. And as you can see, the spring is hanging by a hook. Now what I'm going to measure is I'm going to measure the length of this spring, and that gives me about 6.5 centimeters. Gives me 6.5 centimeters. And let me just explain what's going on here. The spring is an example of a restoring force. So here's the slide that we have in your presentation. You'll notice that a spring, if it's compressed, will actually exert a force to the right. So if I compress to the left, the spring force exerts a force to the right, and I'll just put the full show in full. So when I compress the spring, the mass compresses the spring. There's a force by the spring on the box to the right. Now, if I stretch the spring, then I claim that the spring exerts a force. If I stretch it to the right, then it has a force applied to the left. So the spring force is an example of a restoring force. Now let me show you what that means. So I'm just going to get out of this show and show you what I have here. So let's go ahead and bring my graph up. So I have here the spring attached to the force sensor. The spring measures unstretched 6.5 centimeters. And what I'm going to do now is I'm going to add some weight to it. And what you will see is that the weight acting is going to stretch the spring a certain distance. Now, what does that mean? Well, if I attach a weight to it, then the spring will stretch. But which way is the force going? The answer is that the force is heading up this way, so that it just balances the weight of the object. So if I go ahead and I do another reading of the force, let's go ahead and do that. I'm going to collect, and I'm mostly interested in the force. So I'm interested in the force, and I'm going to try and zoom my camera out a little bit. So just give me a second. Okay, so you see that the spring is stretched. Now we said the initial stretch was, the initial length of the spring was 6.5 centimeters. I'm going to show you the force, so I'm mostly interested in that. I'm not interested in the acceleration. The acceleration I already know is that's gonna be. It's gonna be 0 because the thing is not moving. So let's go ahead and arrange this, auto arrange, so you can see that now, and I'll blow the graph up. And let's clean that up a little bit. So I want 0. And here you see the spring force, the force acting on the spring. If I take an average, which I will do now, and let's go ahead and say statistics. The force acting is 0.486 newtons. So the unit of force is newtons, of course. And let's go ahead and measure the actual stretch. So we said 6.5 centimeters is the original. I have a 50-gram weight on here. And now my spring's length is 9.2, let's call it 9.3 centimeters. Again, I'm measuring from coil to coil, not the weight itself. So now I have a weight, I have a stretch of 9.3 centimeters. Let's go ahead and add a little bit more weight to it. So I have here a 100-gram mass, and I'm just going to add that to my spring and look at what happens. Let's take a reading of that. So I'll store the latest run, and I'll take another reading. Now the spring shouldn't be moving that much, but unfortunately there's a little tiny bit of air currents in the room and so on. I'll just steady it as much as I can. Here is the new reading on the spring after I added 100 grams. So I incremented by 50. So let's go ahead and do another average and analyze. No, cancel. That's not what I want. Latest on that. So this latest force, let me move things around so we don't get confused. The latest is 0.9799. Let's call it 0.980. Call it 0.980. Shouldn't be a huge surprise because the mass is actually exerting a force due to its weight. This is a 100-gram mass, or 0.1 kilogram mass, multiplied by 9.8, and you should get 0.98 as the force. The stretch is rather interesting because if you look at the stretch, I have a stretch of about 13.5 centimeters. Okay, so I might start writing these down. So at 0, so here at 50 grams, I got a stretch of about 9.3 centimeters, or 0.093 meters, whichever you like. In this one, let's go ahead and attach another text to it. Insert text, and I'm going to move this up here, and I claim that this, let's do it one more time just to make sure we get it right. From coil to coil, I call this about 13.7 centimeters. So this was 9.3, this is 13.7. Not XM, but CM. This was 9.3. And I'm going to move this backwards so we can see all of the there we go. 13.7, 9.3. So I'm going to take one more piece of data. And this one is going to be, I'm going to add the 50 gram that I took off. So I'll add that 50 grams. So there's the 50 grams, and let's take another data reading. So I'll do another data reading, and let me just go ahead and save this other data. Show, let's see, store latest run. There we go. So now I have one more data reading I need to do. Let's go ahead and click collect. And there you have it. Look at this. It's almost at 1.5 newtons. So here's the data for the third increment of mass. Now I could probably add one more, but I want to be careful because there's what is called the elastic limit, and that is where you stretch the spring to the point where it can't restore itself. That's called the elastic limit. If you have a car, if you let your car shocks go south, I use them over and over and over again. Eventually, you will reach that elastic limit where those springs, which is what shocks are, will not restore themselves the way they used to. So I'm going to store the latest run, and now I'm going to run a analysis on the force. So that's going to be run 3, and I'll click OK. And so here's my third force, which I call 1.47. And this is at, I'll put a text box up here so that we can see everything. Let's see the stretch now. So I'm going to put this box over here, and I'm going to measure the stretch of the spring. And again, I'm measuring the stretch from coil to coil. You should keep this in mind because you'll be doing a lab very similar to this. Looks to me (18.5 centimeters). Okay, so there's my stretch for that. And again, I will move this to the back so we can see all the numbers. And I'm going to take those numbers down. So I have 8.5, 9.3, and 13.7. So let's make sure everybody's where they're supposed to be. 9.3. This one was 13.7. This one is 18.5, and I'll just make the box small enough that I can leave it. So I have the following. At 0, I left it at 0. At 50 grams, I had a stretch of 9.3. At 100 grams, I have a stretch of 13.7. You might want to write this down too if you're watching. And then I have, for the last mass of 0.15 kilograms, I have a stretch of 18.5 centimeters. Now the point of this is that the force due to a spring is called the elastic force. This force is dependent upon the stretch or compression. And what we're going to do is we're going to make a new plot. So I'm going to save this, and we're going to make a new plot. Let's see. Okay, so I'm going to call this spring 1. And save. And while I'm at it, I will take down the forces so that we have that done. So the mean at 0 is 0. At 0.05 kilograms, it's 0.489. And you can already see the numbers on this video. You can stop the recording and record the max and min, and you can go ahead and determine the uncertainty for each of these forces. I will leave that as an exercise to you. 0.979, 0.980, I'll call it. since it rounds up. We have 3 significant figures, and the last one is 1.47. And these are in newtons. So the mass was in kilograms, the force is in newtons, and the stretch is in centimeters. We can convert that. So we'll do that in the next in the next notebook. So I'm going to go ahead. I saved this as spring1.cbl. I'll open up a new one. I'm going to disconnect the sensor because I'm just going to plot. So let me go ahead and disconnect the experiment, remove interface. So I'm shutting Kepler down. And now I'm going to show you a couple little tricks with LoggerPro, because we're ultimately going to get that, and you can use it. So I'm going to call this the stretch, and I'm going to call it nope, I'm going to call it length. Call it L. Meters. So we're going to have to convert all that stuff to meters. Done. So what I've done is I've named my column. Now I'm going to create another, I will have to create a couple more columns for this to go. I'm going to call this stretch, and short name is delta L. Units are again in meters, so I'll have to calculate that out. Done. So now the LoggerPro only gives you 2 columns, so I need a couple more columns. So I'm going to actually add a new manual column, which I am going to call mass, M and kg, and then I'm going to do one last one. So just give me a second. New manual column, which I'm going to call the force. F newtons, and I'll click OK, click done. So let's stretch out the table right now. See, the nice thing about LoggerPro, and you could do this on Excel as well. So I am going to put in the lengths in meters. So remember that 100 centimeters is equal to 1 meter. So if I want to convert this, I'm going to have to divide every number I say by 100. So 6.5 centimeters becomes 0.065 centimeters. The stretch is 0, the mass is 0, and the force is 0. Okay, so I'm going to add another piece of data to it. 9.3 centimeters, 0.093, 0.093. So that's the length of the spring with the weight on. And what I'm going to do now is 0.093 minus 0.065. Need a calculator. Sorry about that. .028 is the stretch. The mass was 0.05 kilograms. And the force was 0.489. Not a huge surprise because that's actually the weight. If you multiply 0.05 by 9.81, you should get that number. So the next one is 0.137. The stretch is now 0.072. The mass was again 0.1 kilograms, and the force was 0.980 newtons. Not a huge surprise again. The last length that I have is 1.47, I'm sorry, 18.5, so that's 0.185 meters. 85 meters. The stretch is 0.12. The mass was again 0.15 kilograms, and the force was 1.47 newtons. Okay, what's the point? I am going to make a graph. I am going to make a graph of the force versus the stretch. So over here, I'm going to call this the force, and over here, I'm going to call this the stretch. And let's go ahead and hold, please. All right, so after configuring and doing a little auto scaling, you can see in green, let me bring this back, you can see in green, these are my data points. The stretch is on the horizontal axis, the force is on the vertical axis. Now, what am I determining here? You notice that it's going to be a line. As a matter of fact, I can go into analysis, and you can do this on Excel as well, and I'll do a linear fit. So the force is given by a linear equation. Let me blow that up so we can see it. 16. There we go. I like it a little bigger. Anyway, there we go. So here's the force. This is the force acting on the magnitude of the force acting on the spring. And you'll notice this constant here, the slope, 11.97, so it's almost 12. We could call it 12 and not lose a lot of sleep, is called the constant of proportionality. What this graph has proven is that the force is proportional to the stretch of the spring. And as a matter of fact, since it's acting the opposite way, we can call it F equals minus kx. So let me write that down. I'll insert text annotation. Force equals minus kx. So the force is proportional to see if I can move this. The force is proportional to the stretch of the spring. This constant of proportionality is 11.97 newtons. This is called the spring constant. It is also referred to as the stiffness of the spring. The higher the force constant, the stiffer the spring. So this was my discussion on the spring force, and I review with you that the force is always acting opposite. I'll do one last thing before we part. I want you to actually see what the result is. So I'm actually going to save this document. File, save as, and I'll go force versus stretch. Okay, so there it is. That's in my logger files. And now I'm going to turn on a new one, turn out a new file, and I'm going to connect my wireless sensor again. This is Kepler. So I'll connect that up. And I actually want you to see what this does. So I have the force, and I'm going to take all the weight off. I'm going to zero it. Here's my zero. I'm going to put the 100-gram mass back on. That should do the job. And I know that the force is proportional to the stretch. So I could actually go back, measure the stretch, and say, okay, here's the constant of proportionality. It should be about 11.97, almost 12. Call it 12, if you will. So now what I'm going to do is, let me just angle the camera a tiny bit, because I want you to see what this is going to do. And I am going to put it in motion. So now I've zeroed this, and I'm going to give it a little compression, about 5 centimeters, not much. And I want you to see what it does. There's my compression of the spring. And now I will let it go. And let's click record. Notice that the mass is bouncing back and forth. Let's take a look at the graph now. So I have this done. If I auto scale, and I'll just get rid, well, no, I will not. I'm going to zoom in on a little piece of this. Okay, here's what I do want you to see. Here is the force acting, and I'll just take a little piece of it. There we go. And I'm going to insert a graph of the acceleration. And between 4.5 and 5 seconds. So I'm just going to take a piece of this. So I want you to see something rather interesting. So I'll just leave this here. The acceleration will be in the same phase as the force. Actually, it'll be opposite. You'll notice that if we zoom out again, that this is a sinusoidal force. We will talk more about this in chapter 12, I believe it is. But this is the oscillation of the mass, and I can actually get an equation for it. So I'll analyze, and I will carry out a curve fit. And with this curve fit, I am interested, it seems to me that it's on the order of a sine wave or maybe a cosine wave. So let's do the cosine. So let's do that. Try the fit. Zoom in. So I took this little piece, and I'm going to go ahead and zoom this for you. Look at that. What I've got is A cosine BT plus C is equal to the force. It's a cosine function. Okay, and you can actually model the behavior of the mass on the spring based on this cosine function. That's a little TMI for you guys. I'm sorry about that, but I figured that would be worth it. All right, thank you very much.